Working with direct variation is mostly about understanding what the language means. So anytime we see y varies directly as x, we want to remember that what that means is y is equal to some constant of proportionality or variation constant k times x. We can understand direct variation by comparing this to y equals mx plus b, which is a more general form. This is anything linear. In the case of y equals kx, we can see what's missing is the plus b, so that's equivalent to saying plus 0. So in direct variation, what we're saying is that there's a linear relationship and that has a y-intercept of 0, which is another way of saying it passes through the origin. Here we have an example of a linear relationship that passes through the origin, which has to do with time it takes for the sound from the UT tower to reach you, so those chimes from the UT tower, and how far away you are. If you are in the tower, then it takes 0 seconds for the sound to reach you, and you are a distance of 0 meters from the tower. We can use any point to find k, any point other than 0, 0. Even though k really is the same as the slope, we only need one point in order to find it because we already know one point based on the fact that it's direct variation. We already know the 0, 0. So to find k based on a value of x and a value of y, we just plug into the relationship y equals kx. So I'm going to put this down as 680 as my y is equal to k times 2 as my x. Divide both sides by 2, and I get that k is equal to 340. So that tells me my rate of change. I can either plug these x values in to find out what y is, or just see that each time x increases by 1, y increases by 340, and figure out these two values. 680 plus 340, I believe, is going to be over 1,000. It's 1,020. So the value of k is 340. We just found that. And to explain the meaning, we really need to know its units. A rate of change, which is the same as the constant of proportionality in this case, has units of change in y over change in x. We can also look back at this calculation that we did here and see that we got it by a y value, 680, which was meters, divided by an x value, 2, which was seconds. And therefore the units of this are meters per second. Once we have units, it doesn't take long to figure out what's going on here. The only thing that's actually moving is the sound. So this must be the speed of sound. The speed of sound is not totally constant. It changes according to environmental pressure and conditions, but it's approximately 340 meters per second. Now, when I was an undergraduate, I did not go to UT, but I went to Berkeley, and we had our own UT tower, which we called the Campanile. And sometimes on the phone with a friend, one of us would hear the chimes first from the tower itself and later through the phone, or it might even go in the other order. You hear it through the phone first and then you hear it from the tower second. Figure that the sound transmission through the phone is so much faster than the speed of sound in air that you can pretty much neglect it. We would calculate who lived closer and by how much based on that, because of course we were nerds. But that's what made me come up with this example here for the UT tower.